Yesterday, remember, we left off discussing Maxwell theory, and I want to pick up that discussion and discuss its higher form symmetries. Are there any unanswered questions from yesterday? All right, so we'll continue in the same mode. If you have questions, just interrupt me, and then I guess we'll also have a Q&A session later. All right, so just as a reminder, we're discussing free U1 gauge theory, Maxwell theory. This is a theory of a U1 connection, A, and its field strength is F, the action is quadratic, and the equation of motion is this one, d star F equals 0, and the Bianchi identity is just a consequence of the fact that F is dA. And so I'm going to review some elementary facts about this theory, and I'll also quote some results of computations in this theory. This is a free theory. It's a Gaussian theory, so you can compute everything under the sun. And this is something you learn in quantum field theory, and it involves dealing with the gauge fixing and all sorts of things. And if you want to, connect what I'm saying to what Alberto is telling you, then try to apply whatever he's teaching you to do these computations and check the results that I'll quote. Okay, so where did we leave off? So these I'd already said that these closed two forms here will give us the higher form symmetries we're after. But before I get to that, I just want to briefly mention an important property of Maxwell theory that is important from many points of view, that is also important for understanding, for example, its non-invertible symmetries, but occurs in many other physical concepts, and that's the notion of duality. And it's also an example of the general principle I mentioned yesterday, which is that the presentation of a theory in terms of its gauge group may be ambiguous. In other words, the same theory might have two different descriptions in terms of different gauge fields and different gauge groups, and this is a mini example of that. Because here we have formulated the theory in terms of the gauge field A, and F is dA, but as you might know, there's something called electric magnetic duality, or S duality in string theory. It's usually called S duality, which, roughly speaking, exchanges F and star F. And I'm not going to derive this duality for you, but I'm going to tell you what it does and make a few comments. So the derivation is relatively straightforward. It involves manipulating Gaussian path integrals, but it'll be a bit of a detour to do it given what I want to talk about. All right, so what's the S duality map? Well, if you remember that F contains the electric and magnetic fields, in Lorentzian signature, this map sends E to B and B to minus E. This is in terms of physical E and B fields. If you're working in Euclidean signature, there's a funny I that occurs, and the map looks like this. Maybe I'll write it this way. All right. So this F here is the F in terms of which I formulated my theory. This F tilde is a new gauge field. That is the field strength of a different connection called the magnetic dual connection. This A tilde has nothing to do with this A. And nevertheless, you can write this theory as a Gaussian path integral over A. You can write this as a Maxwell theory for A. You have to flip the coupling constant in some way, and the observables map in an interesting way, interchanging E and B, but otherwise the theory is exactly the same. Okay? So this is a baby example of duality. And I wanted to remind you of this because it occurs in many examples, and also because it'll give us a good way of thinking about the electric and magnetic one-form symmetries of this theory. By the way, this funny factor of I in Euclidean signature is related to this minus sign in Lorentzian signature. And one way to think about it is that that star squares to 1 in Euclidean signature, but it squares to -1 in Lorentzian signature. So that's why it's there. Yeah?
Is it obvious that A tilde exists? Because we do the mapping in terms of F, right?
No, I mean, it's not obvious, but it's true. It's true that I wrote for you the mapping of F, but the way you derive this duality is by actually introducing A tilde as an explicit field in the path interval. And so then it's there. Yeah. Yeah, but you're right, it's a priori not obvious. But and you see that the gauge transformations that act on A tilde have nothing to do with the gauge transformations that act on A. So you should think of the gauge group of this tilde gauge theory as being unrelated to the gauge group of this theory, but nevertheless all the gauge invariant of this one both agree. So now let's get to the higher form symmetries. So let me remind you from yesterday that a P-form symmetry, at least a continuous one, is associated with a conserved P+1 form current. Yesterday I wrote this in components. And then, using that P+1 form current, you can do, integrals over closed surfaces of the right codimension to get topological operators in Euclidean space. So let's do that for the two forms that we have in Maxwell theory. So in Maxwell theory, we have P equals to 1. We're talking about one form symmetries. And clearly we have two different ones. And one of them is called the electric one, and one of them is called the magnetic one. So remember that in order to get from this conserved current to a conserved charge, you need to integrate this closed form over a surface of suitable dimension. And since J has dimension P+1, this sigma has to have dimension D minus P+1, or codimension P+1. And then the same argument as we discussed for zero form symmetries last time will tell you that this operator or this charge is topological. And then if you wish, you can also exponentiate it to get kind of generators that depend on a U1 angle. But in this case, you can just work with the charges. Okay, so let's look at the two currents. We have an electric current whose star is I over E squared star F. This prefactor in principle is not fixed by demanding a conserved current, but I'll tell you in a second why I'm putting it there. So I'm writing exactly this form here. And then the star of the magnetic current is just 1 over 2 pi times F2. And of course, these are both closed, and therefore we get an electric charge and a magnetic charge. Both of them are topological surface operators in 4 dimensions. They're codimension 2. Very good. Now, the reason for picking precisely these prefactors in order to define the charges is that it turns out that that's the correct definition to make these the standard integrally quantized electric and magnetic charges of the theory. This is perhaps more obvious for the magnetic charges in Euclidean signature than the electric ones. The reason, as we discussed last time, is that for U1 connection, this quantity 1 over 2 pi times F always integrates to an integer if sigma 2 is a closed surface. Okay? So if we take Q magnetic, which is obtained by integrating this, and then an integer. For Q electric, things are not quite as obvious because the integrality doesn't trivially follow from such a topological consideration. There's also the funny I, which is the Euclidean signature, but you can check explicitly, I won't do it right now, that if you act with this normalized electric charge on these things that we'll soon learn about being the charged objects under this, then you will also get the picture. And if you translate this back to Lorentzian signature, then this electric flux integral, in fact both of these flux integrals, become the standard vanilla Gaussian flux integrals that you learn about in elementary electromagnetism. In other words, they'll become the integral over a surface of B perp or E perp in Euclidean signature. Any questions? Okay, very good. Yeah.
So with this just very elementary last thing you said, it feels like I'm really thinking about something in 3D in a surface, and I'm looking at the normal flux. But here you could dimension 2.
Codimension 2 in 4-dimensional spacetime,
Okay.
which is the same as being an ordinary surface in 3 spatial dimensions. If you forget about time, then you're talking about surfaces in R3, which is the usual setting for Gaussian flux integrals.
But if I move just a little bit before or after in time, my surface should just vanish. Okay.
No, I mean, on the contrary, that's sort of the advantage of this presentation, is that even in you can deform it arbitrarily, even in Euclidean time. So you're not just allowed to deform them in space, you're allowed to deform them in space-time. One thing you can do, for example, is just move them up and down in time, and that shows that they're conserved. But you can also do other things. So this is a little bit more general than that. Now, this action of S-duality on E and B tells you that S-duality also flips electric and magnetic charges, although with a minus sign, such that if you apply S-duality twice, you don't actually get the charges back, you get minus the charges back. So this is an interesting and common feature of duality, which is that it doesn't quite square to 1, it squares to a symmetry of the original theory, which in this case is the charge conjugation symmetry that negates all the charges in the gauge field. Okay, very good. One comment, especially if you read large parts of the physics literature, people often refer to the electric one-form symmetry, which is present in many theories, both abelian and non-abelian. They will refer to this as the center symmetry. Roughly speaking, because it is associated with the center of the U1 gauge group, which is of course also U1. In this case, everything is U1. But this notion is all over the literature, and you should remember that a center symmetry is an electric one-form symmetry. So you can translate that notion easily. All right. Very good. So let's talk a little bit more about the things that are supposed to carry charge under this symmetry. After all, when we discussed zero-form symmetries, there were 2 ingredients to the picture. They were conserved currents and charges, or topological charge integrals, but there were also operators that actually carried those charges. For example, if you remember the phi field in the O2 model, carry the U1 charge, so when you surround it with the U1 charge operator, then you measure its charge. So that's why we say that this local operator has charge 1 under that symmetry. We've defined here some charge operators living on surfaces, and it behooves us to understand what are the appropriate charged defects or operators that carry those charges. By the way, I should maybe also make a comment about the terminology defects versus operators, because very often I will use them interchangeably, and I'll explain why. So if one is being careful, an operator, nothing in Euclidean signature is an operator. An operator exists the Lorentzian signature, we need the canonical quantization, there's Hilbert space, and then there are operators that act on that Hilbert space. And those operators have to act at a fixed time. So from the point of view of Euclidean signature, there are things that live in a fixed time slice. Now, in Euclidean signature, of course, those things exist, right? Whenever you take an operator, then you can also think about it in Euclidean signature acting at a fixed time. But you can also take the same operator and kind of orient it in all sorts of other ways in Euclidean signature, right? Nothing prevents us from doing that. But when you kind of do that, then you lose the interpretation as being just an operator acting on the Hilbert space back in the Lorentzian signature. Instead, if you orient it differently, you might get into a different Hilbert space from the point of view of quantum mechanics. And when you do that, then people usually call this a defect Hilbert space. And so in other words, if you put some kind of disturbance along time, rather than acting along a fixed time slice in the Hilbert space, then that modifies the Hilbert space, and that's called a defect Hilbert space. Now, in a Lorentz invariant theory, we can always go to Euclidean signature. Anything that you can do in a fixed time slice, you can kind of rotate and also do in a way that makes you think of it as a defect. So defect and operators are in kind of one-to-one correspondence. This is a like baby version of modular invariance or something like that. That's not necessarily true in theories that are not Lorentz invariant. If you study lattice models or condensed matter systems, defects and operators are not necessarily the same. You might have different defects than you have operators. But in a relativistic theory, they're always the same, and you can always do this trick and kind of treat them all together in one go. And so that's why the terminology is kind of used sloppily and interchangeably. But it's good to remember that they're distinct concepts. Okay. Now, in our Maxwell theory, these charge surfaces don't live on codimension 1 hypersurfaces, they live on codimension 2 surfaces, let's say, right? And if you think about codimension, you see that a codimension 2 surface can never link a point in 4 dimensions. So one interesting consequence of that simple statement is that these one-form charges do not act on local operators. That is important for all sorts of reasons. First of all, it raises the question, what do they act on? We'll get to in a second. But the fact that they don't act on local operators is very interesting, because it means that if you have such a symmetry, then you can do anything you want to your Hamiltonian. You can add all local operators under the sun, and it will still be there. That's usually not the case. Usually in a quantum field theory, if you have a symmetry, and then there are some local operators that break that symmetry, and if you add them to the Hamiltonian, the symmetry is gone. That's not true for a one-form symmetry. If it's there, then any local perturbation of the Hamiltonian will maintain it. And so that, in some sense, means that one-form symmetries are much more robust under deformations. Yeah?
But doesn't the addition of charge matter break down for symmetry because the Wilson lines can end?
That's, nothing I've said has charge matter in it yet.
But this is a local operator that you are adding to the Hamiltonian.
My assumption was that the theory has a one-form. There are theories with one-form symmetries. Okay. And in those theories, for example, Yang-Mills theory, pure Yang-Mills theory has a one-form symmetry. And you can take
You mean a local operator built from fields that you already have?
Of course. I mean, yeah. So you're studying quantum field theory X. It has a list of fields, it has a Lagrangian, it has a lot of local operators. In general, when you add the local operators to the Lagrangian, they will break all the symmetries. If you take the O2 model and you add a generic linear combination of phi to the Lagrangian, then this will not have any symmetries. So that's qualitatively different from one-form symmetries. Of course, there are some theories that just don't have one-form symmetries to begin with, and then there's nothing to say. Although even there's something to say, which has to do with how they emerge in some limits, but maybe I'll say something about that later. Okay. So, the objects that are charged under these symmetries, by analogy with this picture, are supposed to be able to link with them in Euclidean signature. And so that means that in 4 dimensions, they have to be one-dimensional defects, one-dimensional operators. They have to be line operators. And the things that are charged under the electric and the magnetic one-form symmetries are the Wilson lines and the so-called 't Hooft lines. Lines, line operators, line defects. And the Wilson ones are the electrically charged ones, and the 't Hooft ones are the magnetically charged ones. Of course, you can make combinations of them that are charged under both. Okay, so let me remind you briefly what a Wilson line is. Both of these you can think of as the sort of operators in Maxwell theory that describe the presence of an infinitely heavy external probe particle of either electric charge or magnetic charge. Not a dynamical particle, that would change the story significantly, but just an external probe. And the way we model this probe, if it has electric charge Q, for instance, let's start with the Wilson line, is by inserting into the path integral the following holonomy phase factor. Where Q is the electric charge, and because we're in U1 gauge theory, this charge has to be an integer in order for this to be a gauge invariant insertion into the path integral. So this is some curve. I can take it to be a closed curve in Euclidean signature, in which case it's obviously gauge invariant. I can also take it to be an open curve that goes off to infinity. And in that case, it also is gauge invariant. Just to make contact with the defect versus operator discussion from before, if you think of Euclidean time as kind of going this way and this being space, then a Wilson line that lies in this time slice is an operator. But for example, if you consider some Wilson line that goes along time like this, then that's a defect. And when you quantize this system with the Wilson line going along time, then you're not describing the empty vacuum, you're describing Maxwell theory in the presence of this point charge of charge QE. So that's a defect Hilbert space. Very good. So,
Sorry.
yeah.
Could you repeat again what it is physically? I don't quite understand. The Wilson line.
The Wilson line?
Yeah, what it physically means
Well,
if you had it in space time.
You mean if you have it, if you put it along, let's say, the time direction, or so if you put it along the time direction and you quantize in Lorentzian signature, what you will get is a Hilbert space that, so the usual Hilbert space of Maxwell theory just contains photons, right? There's nothing charged there. 1 photon, 2 photon created by F from the vacuum. The ground state of this, so let me get rid of this part of the picture. The ground state of this Hilbert space has electric charge because you're forcing the Wilson line through the system and you're putting in QE units of electric charge. You can see this explicitly because if you put this A along time, then you'll get A0 here. And when you integrate out A0, you see that you get a charge density that's localized at the origin. So the Wilson line serves as an external source for the electric field. Very straightforward. The Gauss law gets modified so that there's a delta function on the right-hand side. This is electrodynamics 101. And therefore, you're describing a sector of the Hilbert space, a superselection sector that has electric charge QE. And these superselection sectors can never be changed by acting just with local operators. So you cannot act with photons and create this electric charge, but the Wilson line defect can do that. And in general, inserting any defect, whether it's a line or a surface or whatever, a long time, changes the sector of the Hilbert space that you're in. So, unsurprisingly, this, given what I said about Gaussian flux integrals before, this Wilson line of charge QE is precisely the thing that carries charge QE under the electric one-form symmetry. Right, remember that I told you that the electric one-form symmetry is just the electric Gaussian flux integral over a two-sphere or a codimension two-surface linking the line. Very good. So, and in principle, one can check this explicitly by computing this correlation function, the correlation function where Q encircles the Wilson line. Very good. So these are the electric charge things. These are perhaps somewhat familiar. Now, based on what I said about electric-magnetic duality, there have to be magnetically charged line defects as well. And it's easy to think of them as Wilson lines of the magnetic dual gauge field, A tilde. But it's also nice to describe them directly in terms of the original presentation of the theory. And there they look very different because the Wilson line was a very nice kind of insertion into the path integral, which could be written as a standard local function of A. So it looks like a pretty benign modification of the path integral. The 't Hooft line, which is supposed to describe a magnetically charged probe particle, is defined differently. It's defined in a way that people refer to as being a disorder type insertion. So the way one does this, remember that the only way to get magnetic flux to appear in Maxwell theory is to have a two-cycle somewhere. You have to have a non-trivial two-cycle in which this magnetic flux can live. And the 't Hooft line is supposed to precisely carry this magnetic flux. So if this is the 't Hooft line of magnetic charge M, then the way you define it in space-time is, so imagine this is time. And imagine you zoom in on a spatial slice. The spatial slice is R3. As we discussed before, in R3 this just looks like standard electrodynamics. So you have a magnetic charge at the origin, and you would like to describe that. And in order to put magnetic flux around the origin, one thing you can do is you can sort of drill out a tiny hole around this point. You can cut out a sphere of radius epsilon. And you know, if this smells like a kind of UV regulator, it is, because all of these are kind of highly composite operators, so they require UV regularization. And so when you define the 't Hooft line, you have to cut out this little hole, and then you have a sphere of finite radius on which you can put QM units, of magnetic flux. And notice that the moment you cut out this sphere, you change the dimension of the defect. The defect is supposed to be a line, but when you blow up the sphere, you kind of make a tubular neighborhood of the line, and you actually have a codimension 1 surface. So now you're in the situation that Alberto was discussing this morning, where if you study Maxwell theory in the presence of this surface, you have to put boundary conditions to get a well-defined theory. And the boundary conditions you put is precisely to put a uniform magnetic field of charge QM on the sphere. And then you shrink the sphere back down, and then you create this line defect that carries magnetic charge. So this might sound very, very different from the way that this is defined, but it's exactly the magnetic friend. And in this presentation, it's essentially obvious that this loop carries QM units of magnetic one-form charge because it was defined in this way, right? We imposed the condition that the flux integral over this sphere is QM. Any questions? Very good. And as I said before, if you want to make a a line that carries both electric and magnetic charge, what you can do is you can take Wilson lines and 't Hooft lines and fuse them together. Just like you can fuse local operators together in the way that it's done in the OPE, you can also fuse line effects. And then you get dionic lines of magnetic and electric charge, and all sorts of interesting things happen to them. For example, they might have different statistics than the Wilson and the 't Hooft line because of the Dirac angular momentum in the field when you fuse them. All right. So this is very basic, and because it's a quadratic theory, all the equations are essentially classical, and they are the classical equations of electromagnetism, so they're familiar. But one kind of learns a lot of things about one-form symmetries by thinking about this example. And one of the most important sort of slogans or intuitive messages is that you should think of one-form symmetries as flux conservation symmetries, right? Here they really just measure the electric and the magnetic flux of the lines, and the fact that these symmetries are conserved, the fact that these charges are conserved, means that we can move the Gaussian surfaces up and down and we can deform them, and the value doesn't change. And in particular, this is related to a point that somebody already raised, these lines cannot end, right? Because if they ended somewhere, then you would be able to slip this topological surface off and it would just measure 0. So that's what I mean by flux conservation symmetry. The flux just has to keep going so that it can go along the line can move, but it can never end. So conversely, if there is a way to end either all lines or some lines, that means that the one-form symmetry will be ruined. And of course, that's what happens in more general examples. In this example, in this theory, no lines can end because there are no charged fields. There are no local operators other than the photon. The photon doesn't carry any charge, and so none of these lines can end. Very good. So that's an important slogan. The thing I want to do now, before getting to more complicated examples that actually have some lines that can end and that have a smaller one-form symmetry, is I wanted to say something about, I wanted to make contact with the discussion of phases and the Landau paradigm, because we had a discussion about how, the realization of standard zero-form symmetries allows you to classify phases of field theories or of statistical systems. And one of the important things about higher form symmetries or generalized symmetries is that they also allow you to do this. And they apply, they give you a kind of Landau style interpretation of various phases, in particular gauge theory phases, that would not have a conventional, that would not fit into the conventional Landau paradigm if you only restrict yourself to zero form symmetries. And so let me first discuss this just in pure Maxwell theory. Of course, this theory only has one phase because it's a free field theory. So it's a gapless theory with a photon. But nevertheless, we can ask, how are these one-form symmetries realized in this phase? Remember, the question that Landau asked is which symmetries are there to begin with? And then in phase X, are they unbroken or are they spontaneously broken? That's essentially what we have to understand. And the question is, in Maxwell theory, are these symmetries broken or not? Okay? Now, it turns out that in Maxwell theory, there's a trick to answering this question, and then there's a slightly more long-winded and general discussion as well, which I'll maybe cut short a little bit. The trick involves the following observation, which remember we made in the context of the O2 model yesterday, but it applies in general to continuous zero-form symmetries. which is that if you have a current, a conserved current, and that current, when acting on the vacuum, creates a single massless boson, one massless boson. More precisely, you'll create a one particle state of some momentum, some wave function that's proportional to the momentum. Then the symmetry that is associated with this current must be spontaneously broken. And this massless boson must be the associated Nambu-Goldstone boson. So this is a Nambu-Goldstone boson, and this symmetry is spontaneously broken. By contrast, if you are in a phase where the symmetry is not broken, this current, when acting on the vacuum, it'll also create stuff, but it'll create 2 or higher particle states. It will not create a single massless particle state. And so with this in mind, this slogan also applies to higher form symmetries. This is if you wish, this is a subcase of Goldstone's theorem. If you look up the proof of Goldstone's theorem, this argument will appear at some point. And if you remember from down here, right, that the electric and magnetic currents are just proportional to the photon field itself. They're linear in the photon field. Right? The photon field itself is just a linear combination of A's and A daggers, and when you act with it on the vacuum, it will just create a one photon state. And so that means that these higher form currents in Maxwell theory, when acting on the vacuum, also create just a single photon. So in Maxwell theory, J electric and J magnetic acting on the vacuum create a massless photon. Now the photon has spin 1. It's a vector particle, unlike these Goldstone bosons here, which are spin 0. That's related to the distinction between this being a vector current and this being a 2-form, right? But nevertheless, you get a single massless boson, and that means that these symmetries, these one-form symmetries, are both spontaneously broken. So both U1 electric and U1 magnetic is spontaneously broken. And the photon, with its 2 polarization states, is the associated Nambu-Goldstone boson, the generalized Nambu-Goldstone boson for this, with its spontaneous breaking. So that means that one can think of pre-Maxwell theory as being in a phase where its generalized symmetries are spontaneously broken. And that's a good way to characterize the phases of gauge theories that have free photons in them. And we usually call them Coulomb phases.
Sorry, why are they broken? Because there's a massless photon, or?
Well, the fact there's a massless particle is necessary, but it's also important that it's created by acting with a current. See, if the current had been bilinear in the creation operators of the massless particle, that would not have broken the symmetry spontaneously. It's really the fact that the current is linear. So this is the quick and easy way to convince yourself that this is true. But let me mention a slightly longer and more principled way of doing it as well, without necessarily going into all the details. This trick is correct, and it works even for zero-form symmetries. But remember that for zero-form symmetries, there was a more primary way of thinking about whether or not a symmetry was broken, which was simply to ask the question of whether the charged field got a vacuum expectation value or not. Right? Remember that in the O2 model we had a complex scalar field phi, And the question we asked is whether this is 0 or not. And if this is not 0, if this complex field gets a vacuum expectation value, then the U1 symmetry is spontaneously broken. We're in the broken phase. And on top of that, there's a Goldstone boson. But the primary thing was that there was a charged operator that got a VEV. And it turns out that this notion also exists for higher form symmetries, for one form symmetries in particular. Here the charged operators are these Wilson and the 't Hooft lines. And so you might ask, what does it mean for a Wilson and a 't Hooft line to get a VEV? And that's a slightly long-winded discussion that involves a few technicalities that I would like to kind of bypass. I'm happy to explain it later. But roughly speaking, what it boils down to is to ask the question of what happens when you take a Wilson or an 't Hooft line and you make it very large. So let me start with the Wilson line. Of course, with the 't Hooft line, it'll be exactly the same. And if you take a closed Wilson loop and you make it very large, then you can ask how it behaves at very long distances as you take its size to infinity. The simplest cases are to take a circle or a square, but in principle, any reasonable shape. If you take this to infinity, then there are, roughly speaking, two different qualitative behaviors. Either it can decay, so that as you go to infinity, you just get 0. That's the sort of normal behavior that we expect of correlation functions. If you take a correlation function and you go to infinity, then it'll cluster and give you 0. The only exception to this rule is that correlation functions don't go to 0 when something has a VEV. Right? If you think of, for example, the 2-point function of phi, and you apply this logic to it, if you take the 2-point function of phi, in a phase where phi doesn't have a VEV, then it clusters and it decays to 0 at infinity. But if phi gets a VEV, then the limit of the correlation function, the 2-point function as you go to infinity, is the VEV squared, and it's non-zero. And so that's a signal of symmetry breaking. And the same logic applies to loops. It takes a little bit of an argument to show this, but it's true. And so if you take the loop to be large, which I'll schematically denote by saying that C goes to infinity, and then if the loop decays to 0, that's like having no VEV, that's like having a decaying correlation function. And in that case, the symmetry is unbroken. And the other option is that you get a VEV, a non-zero VEV for the loop, a non-zero number, which doesn't decay away. And that means that the symmetry is spontaneously broken. And you can verify, I will not do it here, that in Maxwell theory, the Wilson loop indeed does not decay away. If you look at large loops, they have a non-zero value when you make the loops large. And that's a consequence of the fact that the Coulomb potential decays at infinity. When one computes the expectation value of this loop, one is essentially exponentiating the 2-point function of f, because this is a Gaussian theory, so everything can be computed by using the 2-point function of f. And the 2-point function of f, roughly speaking, the Coulomb's law. Since Coulomb's law decays to 0 at infinity, its exponential will be a constant. So that's how this comes about. All right, so this is, as I said, something I'm happy to go into more detail about, but giving all the details here would prevent me from saying a few other things that I would like to get to. Any questions? Yeah.
Could you maybe define what it means for symmetry to be broken in that scenario, and what the difference between a broken symmetry and a spontaneously broken symmetry is exactly?
I'm only talking about spontaneous breaking.
Okay.
Spontaneous breaking is the terminology that physicists use for having a situation where a system has a symmetry. So in other words, the Lagrangian has the symmetry, the path integral has the symmetry, the Hamiltonian has the symmetry. So, but it's realized in this fashion, in the vacuum, that the vacuum doesn't preserve the symmetry, right? So this is the thing that we kind of reminded ourselves of in the case of the Ising model yesterday, which is that it's perfectly possible to have a Z2 symmetric potential and not have a Z2 symmetric ground state. And that's a feature of quantum field theories and statistical systems in infinite volume, which is very non-trivial, but it's true. And so the spontaneous breaking that I'm talking about does not mean making this potential not Z2 symmetric. That's what we usually call explicit breaking or hard breaking. That would just mean that the Z2 symmetry is gone. It's not there, you shouldn't talk about it anymore. There's nothing to discuss. The question arises when there is actually a Z2 symmetry at the level of the potential, or at the level of the Hamiltonian, and you're asking about whether the ground state preserves that symmetry or not. That's spontaneous breaking. There are all sorts of equivalent ways of checking for this. Maybe the most obvious one is to act with the symmetry on the ground state and check whether it's invariant or not. Sometimes that's perhaps the most intuitive, but it's a little bit ill-defined because this operation doesn't actually make sense precisely when the symmetry is spontaneously broken. It makes sense when the symmetry is not broken. When the symmetry is not broken, then the charge exists and it annihilates the ground state, and you can define the exponentiated operators and they preserve the ground state. Precisely in the spontaneously broken case, the charge operator actually doesn't exist. It's actually ill-defined. So it's a little bit imprecise to say that spontaneous symmetry breaking is the situation when the charge doesn't annihilate the ground state, because the charge doesn't even exist. But it's intuitively what happens. The more precise version involves looking at order parameters and correlation functions and so forth. Other questions? Okay, let me say a few things about background fields and anomalies in this model. And then hopefully in the second hour we can talk about models with charged matter. So we've discussed the one-form analogs of lots of phenomena that we know from zero-form symmetries. But one of the things I haven't talked about yet is anomalies. In fact, I haven't talked about the zero-form symmetries either, and I won't because I don't have time. But let me say a few things about anomalies in the context of one-form symmetries. Let me first remind you, in the context of a zero-form symmetry, what an anomaly is and how you detect it. There are many ways to detect it, but the sort of primary one that we typically talk about. Again, there are many anomalies in the universe, and the word is heavily overloaded. So the anomaly that I have in mind is what's now sometimes called an 't Hooft anomaly. And just like spontaneous breaking, that's supposed to refer to the fact that the symmetry is not in any way ruined or destroyed, but that instead it has some kind of interesting features that you can explore. So let me quickly tell you what you would do if you had studied a model with a U1 zero-form symmetry, like for example the O2 model from yesterday. If you have a U1 current, then you can use this to couple your theory to a gauge field, which is a standard U1 connection, but you don't make this gauge field dynamic. You don't do what you do in Maxwell theory. In Maxwell theory, you take the gauge field and then you do the path integral over it. So you're doing quantum dynamics with this gauge field. In this situation, you just want A to be some kind of external classical source. So you just take this to be some prescribed function of spacetime. You do not do the path integral over A. So this is classical, or C number. But what this does is it deforms your theory so that it now depends on A. The Lagrangian depends on A, the action depends on A, and if you do the path integral over the dynamical field, you will get some kind of partition function or other observables that are now functions of A. Now, normally, when you have a conserved current and a U1 symmetry, the conservation of the current is tantamount to the statement that this partition function doesn't actually depend on A, it just depends on A modulo gauge transformations. So normally current conservation is sufficient to ensure that this partition function is gauge invariant under gauge transformations of this classical source. Again, this is a function of a classical variable. This is something you compute by doing the path integral over all the dynamical fields while keeping A fixed. So for example, in the O2 model, you would integrate over phi, but not over A. Now, an Toast anomaly is a situation where modulo some fine print, this is not true, and this cannot be achieved by modifying the theory in any sensible local way. And when this is the case, and the partition function is not gauge invariant, then we say that there's an Toast anomaly. Right? I'm glossing over some stuff here. So for example, it's not true that any violation of background gauge invariance is an Toast anomaly. It turns out that some violations of gauge invariance can be canceled by modifying the theory in a straightforward way, for example, by adding some local terms to the Lagrangian. But the anomaly is precisely the statement that you can't add such terms to make this gauge invariant. So there's no way to make it fully gauge invariant. And there are lots of famous examples. An example, for example, would be a chiral fermion in even space-time dimensions, which would have an anomaly of this sort. So in 4 dimensions, this would be a triangle anomaly. In 2 dimensions, it would be a kind of 2-point function. Okay, so anomalies are great. There's a huge amount of stuff to say about them. I'm not going to say anything about them in the context of zero-form symmetries. But I would like to briefly say something about background fields and anomalies in the context of one-form symmetries. Right? So just like we coupled the ordinary one-form current J to a U1 connection, big A, over here, we can try to couple these two-form currents in Maxwell theory to suitable background gauge fields. And unsurprisingly, the correct notion of a background gauge field would be a gauge field that has multiple antisymmetric indices. So for example, for a one-form symmetry, it would be a 2-index antisymmetric gauge field, precisely the thing that can contract with J electric and J magnetic. In the case of Maxwell theory, you could try adding something like this to the Lagrangian. You could add 2 background fields of this type. Now, these types of antisymmetric gauge fields are more complicated than standard U1 connections, and there's interesting, subtleties associated with them, but they're also very familiar from many contexts. For example, they arise all over the place in string theory. Famously, in 10 dimensions, they're needed for anomaly cancellation, Green-Schwarz mechanism, and so forth. So here they arise as the natural background gauge field, as the natural sources for these currents. Now, the analog of this statement is that we should be able to couple these background gauge fields to F and star F in such a way as to make the partition function invariant under background gauge transformations of these B's. What do these gauge transformations look like? Well, they're higher form gauge transformations. So they take the 2-form gauge fields and they shift them by D over 1-form gauge field. So you see that the gauge parameters for these B's are themselves 1-forms, and in fact they're U1 connections. All right. Now, in the 2 minutes I have left, I think I can explain, roughly speaking, how this works out in Maxwell theory. So we can take the Lagrangian of Maxwell theory, and well, one needs to play around a little bit with it to figure out what the right couplings are, but it's not so difficult to figure out. So we need to write a generalization of the Lagrangian that I wrote before, which only depended on the dynamical gauge field, right? Before I wrote the dA and star dA. And it turns out that the combination in which dA and d electric appear look like this. And as a result of that, little a actually shifts under the electric gauge transformations. And that's very natural because little a is the sort of electric Wilson line. It's the electric gauge field that shifts under these electric gauge transformations. If this reminds you of sort of a minimal coupling type Lagrangian, then that's exactly what it is. So you can check for yourself that this Lagrangian is invariant under this gauge transformation. And if you expand this quadratic term out to linear order in B electric, you'll precisely find the coupling of B electric to J electric that I wrote here. All right? So these couplings to B electric and B magnetic are only true at linearized order in general, and you also have quadratic terms. Sometimes people call them Siegel terms. So these are the terms that you need to add to make the whole thing gauge invariant. So this Lagrangian by itself is fine, but what we're missing is the coupling of B magnetic to J magnetic. So let's write that. In Euclidean signature, it looks like that. You see, B magnetic couples precisely to the magnetic flux density. So this looks like a perfectly good guess. The first term is invariant under these electric gauge transformations. The second term nicely couples to the magnetic current. The problem is that you see that the second term is not quite invariant under this gauge transformation. Right? If you believe me, from ensuring that this term is gauge invariant, you need to assign this gauge transformation to little a. And when you apply this gauge transformation here, you don't quite get 0. You get dm wedge d lambda electric. So what you learn is that under gauge transformations of B electric and B magnetic, the action is not quite gauge invariant. It changes by the following term. You see that this term no longer depends on the fields. All the dynamical fields have dropped out. But it does depend on these background fields and their gauge parameters. This is now a C number. This is now a classical object. It's no longer a field. But you see, it's a non-invariance of the action. And that means when you exponentiate it, it will lead to a non-invariance of the partition function. So this non-invariance of the action or of the partition function signals an anomaly in the theory, and it turns out to be a mixed anomaly involving the electric and the magnetic symmetry. You see that this shift only appears if you turn on B magnetic, and on top of that you do an electric gauge transformation. So it mixes the two symmetries. If you ignore the magnetic symmetry, for instance, you shut this off, set this to 0, and then there's no problem. So the electric symmetry doesn't have an anomaly, and neither does the magnetic symmetry, but there's a mixed anomaly between them. In fact, this mixed anomaly is a kind of close cousin of the anomaly between momentum and winding of a two-dimensional compact boson. The kind of four-dimensional friend of this anomaly. All right, so maybe it's a good time to stop. Are there any questions quickly before the break, or maybe we can take a few minutes break? Yeah.
Is your B field a bundle germ? Action on a bundle germ?
I think so.
You think so?
So the coefficient of a BDA term should be quantized, right? Because, I think the coefficient of this BDA term should be quantized because it's a topological term, it's BF term.
Yeah, it is quantized. It's in the right unit is 1. This is a BF term with coefficient 1.
That's a good question. Sometimes for zero-form symmetries, anomalies show up in the measure of the path integral. So it's not possible to see it just. It seems like we can see it classically here.
Yeah. So that what you say is true for fermions, and for other types of anomalies, for example, involving B fields. But it turns out that for simple bosonic anomalies of this type, they just show up classically. Do any mathematical.
Curiosity. So, when we were checking that the currents interpolate the photon, right? If we are in a slightly different context, like for example in an abelian Higgs model, and then we look at the magnetic symmetry.
We'll discuss the abelian Higgs model next.
Then we will postpone the question. Because it was just like, is it feasible to check that the magnetic symmetry is unbroken by seeing how it acts on the vacuum?
Yes, it's very feasible. We'll do it after the break. Okay, let's take a 5-minute break.